Tuca Auffinger to the seminar, and he'll be speaking about Parisi measures. Please, Tuca.
Okay. Thanks, Sander. Thanks for the invitation. It's nice to talk to IMPA and talk to friends. Okay, so what I'll do today, I'll talk about Parisi measures. This is based on joint works with Wei-Kuo Chen, who's a longtime collaborator. He's in Minnesota. Qiang Zeng, who was a postdoc a few years back, now he's in Macau. And more recently with Yuxin Zhou, she is a grad student here. Okay, so what is the story that I want to tell you? Well, and I'll try to go slow, and please interrupt me anytime. Well, it starts maybe like 60 years ago. People were interested in glasses, and physicists were trying to understand why glasses are rigid in real life, like window glasses, but when you look at a microscopic scale, it doesn't look like a solid. Okay, it also doesn't look like a liquid, and this is still a mystery. Okay, even nowadays. So glasses are, although they're very common, they're not well understood. So 50 years ago, just motivated by the study of glasses, people found magnets that had exactly the same type of structure. And these were called like spin glasses. They are more rare in nature, but they're easier to analyze in labs, in fact, just because they are magnets. And physicists, they start to try to create a theory to explain this phenomenon of why things are being in a stable state, where they actually are in a meta-stable state and work in different time scales. All right, so the first model that they proposed was a model where very simple to describe, which is you just take a Poisson point process in R3. You think these are just particles. And at each, these are just the positions. And then at each position, you just put a spin. Okay, so a spin is just a vector in R3, which is pointing, like, let's say, in a uniform direction. Okay, somewhere. And now you create an energy of this configuration. So these spins, we have n spins, this is called a configuration. So you create an energy, which is essentially a function of the directions of the spins and the distances. But it's a function such that sometimes, depending on the distance, spins want to be aligned. And then you go further out, they want to be not aligned. But this also changes. So you go further out, and then they want to be aligned again. So it's some function that is oscillatory. So it takes positive and negative values several times. And this is what they expect to be the phenomenon they describe as spin glass. Okay, especially the phenomenon that I'll describe in a second called frustration. Okay, so this model has a name. It's called the RKKY model. It was the very first one that was introduced by experiment. I mean, not theoretical physicists. People are actually just trying to do in the lab. And it's just completely open. There is not a single paper about it. Okay, people cannot understand it. Even in physics, people don't understand that model. Okay, so then back in the 70s, came a very first nice idea, really brilliant idea by Edwards and Anderson, where they decided, okay, so this RKKY model is too hard to analyze. So let's do one thing that is much simpler, which is let's forget about random positions. Let's just put all spins in a fixed lattice. Okay, let's say ZD. And instead of having this, since we have randomness in the model, let's just make the energy itself random. Okay, so they decided, okay, let's just write down the energy as, depending on the distance, which is now fixed because positions are just fixed. Sometimes the spins want to be aligned, or sometimes they want to be in opposite directions. Okay, so they just thought, okay, let's take a model where just take the lattice ZD. We put plus or minus one in positions, and then every time that I have a bond, this bond has a Gaussian random variable, and the interaction is just depends on the sign of this random variable. Okay, so that's the EA model. It was the very first simplification of the RKKY model. It is still pretty much a big discussion in the physics community. In the math community, there are very few results. Okay, this was like back in the 70s. So you see like 50 years and still no progress. Okay, then there came another simplification. That's the model that I'll talk about, which is, okay, forget about the lattice. Let's simplify even further. This was given by two physicists, Sherrington-Kirkpatrick, and they decided, okay, forget about the lattice. Let's just look this same model on a complete graph. Okay, so you remove the geometry of the background. You just think that you have any particles in the complete graph, so all spins will interact. And that was the Sherrington-Kirkpatrick model. Okay, when Sherrington-Kirkpatrick wrote their paper, they said, here is a solvable model of spin glass. Okay, so they said, okay, this is a model that we can actually solve, different than the other ones. This is easy to do. Well, it turns out that the solution that they proposed was wrong, and that's where Parisi comes in. Parisi a year later realized that, okay, your model at low temperature doesn't make sense. You have negative entropy. Here's what happens for the SK model. Okay, Parisi's idea and insight, well, it's one of the main things that gave him like the Nobel Prize last year. And my talk is about exactly the functional order parameter, the thing that he discovered that actually describes the model. Is that okay? So that was my brief introduction where this is coming from, because from now on I'll be talking about just real analysis essentially. Okay, so this is coming from physics. So let me just try to describe what is the SK model and what is this functional order parameter that is now called the Parisi measure. Okay, so what do you want to understand? It's very simple. There will be two cases. So I have my configuration space. Oh, sigma n will be either the spins will be just either just plus or minus 1 to the n, or soon it will be just I'll just take this sphere, the n-dimensional sphere of a square root of n. Okay, so on this space I'll just look at a function which is random. So for sigma in my configuration space, what is this function, this Hamiltonian? Well, it'll be just the sum of, let's say, just take a first example, Gij, sigma I, sigma j, where these Gij's are IID standard Gaussians. Okay. What is our goal? Our goal is very simple. Our goal is just try to understand the landscape of this function. And by landscape, I mean just very first question, you can just try to understand the maximum. Okay, so you can try to just understand the maximum, of course, as n goes to infinity. Okay, and try to prove limit theorems for this guy. Okay. Well, it turns out that in this case, it's actually the case that you're dealing with the spherical model. It's very simple because this is a quadratic form. It can be written as just a matrix applied to a vector in a product of the same vector. So you know where the maximum is. The maximum is the top eigenvalue of that matrix. Okay, so that's easy. It turns out that this question on the hypercube on the discrete space is extremely hard. Okay, and that is the first question that I'll try to focus on. So the question is, the goal is try to understand limit theorems for this quantity. Okay, I'll call this guy, I'll define as G sub n. No, ground state. Okay, so what is the approach that you do in statistical physics? Well, one of the approaches, instead of studying the maximum itself, what you do is just study the model at positive temperature. So you study the Gibbs measure. So the Gibbs measure Gn of sigma is just exponentiate beta Hn. I normalize by a partition function just to make this guy a probability measure. And now the Gibbs measure is something that that interpolates. This measure interpolates between well, the case beta equals 0, which is just uniform measure, to the case beta equals infinity, which is exactly the quantity that we want to study. Beta equals infinity. This measure is just it just concentrates the delta mass at the maximum, at the argmax, or possible argmax if there are multiples. Okay, so this will be just delta mass at argmax. Okay. So what you want to do is, and that is sort of like you're just, this is a hard problem. This is like you're making softer, just to try to analyze the Gibbs measure. What you want to understand is what happens between 0 and infinity. So at high temperature, so that beta is the inverse temperature, things are easy to describe. You just have uniform measure. At beta equals infinity, that's our goal. Okay. And other questions, what happens to this sequence of measures? GN. Okay. So here's a brief, okay, so let me just tell you what is predicted. Okay, so here is the prediction. Okay, so first there is something that I'll explain. That is something that we know. That is actually a theorem. Well, number one is that GN will depend only, essentially, you can't describe the whole measure if you know one quantity, which is just the overlap. So let me explain what is the overlap. The overlap is just you sample two copies from GN independently, and you just look at their inner product. Okay, so you just do you sample sigma 1 and sigma 2 from GN square. And then you look at what I call R12, which is just the normalizing the product of these two guys. Okay, so this sequence of measures, n goes to infinity, will actually only depend. So if I can describe a limit theorem for this quantity, then I'll be describing essentially my whole model. Okay. And then it turns out, and then I'll make things precise, that, okay, this R12 will converge let's say in distribution to, okay, so this is a measure on 0, 1, or minus 1, 1. Okay, so it's in the product. So this will converge to a measure, to a probability measure on negative 1, 1. And this guy is what we call the Parisi measure. Okay. So of course, this Parisi measure depends on beta, and that is what I'll try to describe in a second. Okay. Okay. So then, what is the prediction for this quantity? Well, perhaps let me just start with the prediction. So this is 1, 2, and the third. So let me start with just Parisi. Here's exactly what Parisi did. What Parisi did is that he said, okay, what I'll do first, I'll just study the partition function. And I'll write, Parisi wrote the following quantity, is that, okay, if you look at the partition function, then the limit of free energy, so if you do limit as n goes to infinity, this guy is given by a variational problem, on the space of probability measures. So it's the infima over mu, a probability measure on 0, 1 of a certain functional that depends on beta of mu. Okay, this functional you can write. Okay, what is p beta of mu? P beta of mu is I'll write like this. It has a non-linear term plus I'll integrate x squared mu of 0x dx. And there's a second term which is linear in mu, And which is easy to explain. Okay, there, I'm also missing a constant plus log 2. And what is this this phi of beta? Oh, I'm sorry. I think I just lost everything that I wrote. I apologize. So this is the infima of P of beta. These are just probability measures on 0, 1. What is this P of beta? P beta of mu, sorry. This is, again, it's just a non-linear term plus something that it's easy. Where, what is this function? Well, this function is a solution.
Tuca, you had x squared previously in the formula.
Oh yeah, I missed this square. There you go. Okay, so then what is this? What is this equation? Well, this equation is this function phi solves a PDE. So this guy is a solution of the PDE given by phi t of phi is equal to minus beta over 2 phi xx. So far it's just the heat equation plus, but then there's a nonlinear term, phi x squared times mu. Okay, with initial condition, given by phi of x1 equals to log cosh of x. Okay, so so my point is, okay, if this is the first time that you're seeing these equations, you have no idea what's going on. You're probably completely lost. What I'm saying is that, okay, what do you have to do to find the limiting free energy? You have to solve a variational problem on the space of probability measures. So it's an infinite dimensional variational problem. What is the function that you're trying to minimize? It's a function that on the space of measures is something that it's linear. That I think, okay, this is easy. Plus, now this term, which is extremely complicated, because what you have to do is that for a given measure mu, I have to solve this PD backwards, starting from 1. So I need to find the solution of this PD at time 0, at the point x equals 0. And then I plug in. Okay, so that's the game. Once I have that, I have my p beta of mu. And now you have to minimize this over the space of measures, probability measures. Okay, so it's the message here is that, okay, there is an explicit formula for the limiting free energy, but it is complicated. Okay, and this measure here that was predicted to describe the whole picture of the Gibbs measure is, in fact, well, it's given by exactly the minimizer of this variational problem. Okay, so so what I will say is that, okay, the Parisi measure is the minimizer of this quantity. Okay, and of course, this measure depends on beta. And now I can just ask you, okay, probably you won't try to solve this variational problem, but what happens? What is, let me call this measure mu star? Okay, it depends on beta. What is mu star? Like this. What is mu star at beta equals 0? Can you guess? Okay, you forget about this variational problem here. You can just go back to intuition, right? So at beta equals 0, this measure is just uniform measure. Okay, if you believe what I'm telling you, the Parisi measure is the measure that actually describes the following procedure. You sample twice according to the uniform measure, and then you look at the the inner product of these 2 points. Okay. So what happens if I sample 2 points from the hypercube or 2 points from the sphere uniformly, independently of each other, and I take their inner product? What is their inner product? Do you have an answer? You're moving.
I'm not sure the microphone works.
Oh, I can hear you.
You can?
Yes.
Okay, so it's 0.
It's 0, right? So if you sample 2 points uniformly from the sphere and you send the dimension of the sphere to infinity, well, you get exactly 2 orthogonal points. Okay. So the Parisi measure at delta at beta equals 0 is exactly delta mass at 0. Okay. What happens if I do mu star at infinity? Let's say whatever that is. Well, this guy is something that will concentrate on the argmax. If there is only one maximum, which is easy to show, then this guy will be just delta mass at 1. Is that okay? So this will be just delta mass at 1. Okay. Okay. So now, what happens in between is what I'll write next. Is that okay? So here is for the SK model, which is the one that I'm describing so far, on plus or minus 1 to the n. So on the hypercube. So this is the one that was the prediction given by Parisi. Is that okay? Yes.
But the argmax is, I think, your function is symmetric, so your argmax is.
Yes. Okay. So this is 1/2 plus 1/2 delta -1. There you go. Yeah, because I'm tricking you here. I call the Parisi measure the guy that minimize this on 0, 1. So the Parisi measure actually have I'm removing the symmetry in the variational problem. But you're right. Okay, so what is the prediction by Parisi? Is that okay? There exists his prediction that there exists a beta critical, such that the following happens. If I okay, so now I'll write. I like to draw the distribution function. So for beta less than beta critical, then your delta mass at 0. That's the high temperature regime. So you just get this is mu beta. Okay, so this is high temperature, which physicists call this is the replica symmetric. Solution. Okay, but then after beta critical, let me put it here. For beta bigger than beta critical, then for the SK model, then in fact this Parisi measure becomes something that has an absolutely continuous part. Okay, so there is a value Q of beta. There is a jump at the top of the support. But then here the measure is absolutely continuous. Respect to Lebesgue. Okay, and this is what the physicists call the full RSB phase. Okay, full RSB. And of course, when I send beta to infinity, this is for beta being the beta critical. Then this part of the distribution function gets shrinked, it goes down, and this is just moving to 1. Okay, and that's how you recover this measure here that I wrote first. Let me erase the one after I remove the symmetry. Okay. All right. So this is what Parisi predicted. What it's known math-wise. People study this you see, at this point, you can just forget about spin glasses. What you're trying to do is just real analysis, in fact. You're trying to solve this variational problem and try to explicitly write down what should be properties of the minimizer. Okay. So what is actually known? Well, what is known, that's first, there is the work of Eisenman Leibovitz and Well. This was back in the 80s. And then the work of Toninelli back in 2002. What they showed, well, what Eisen, Leibovitz, Real showed is that they showed, okay, so that that this beta critical, oh my God, I did this again. What happened? Can you guys see it? No? No, this? You guys see this? Yes. All right. Okay, cool. Okay, so Eisen and Leibovitz Real showed the existence of beta critical. Toninelli actually determined what beta critical is. Okay. So they showed exactly that exactly that there exists a number such that below essentially showed that exactly that if I draw like this is replica symmetric. This is Toninelli. This is not replica symmetric. Is that okay? All right. Then okay, so here's the first theorem. And then after this, then okay, then there was essentially nothing after 2002. And then myself and Wei-Kuo Chen, this is back in 16, is that we showed that for beta bigger than 27.4 or 27.5, just to be safe, then the Parisi measure, mu beta, has at least 3 points in its support.
Tuca?
Yes.
So in Toninelli's work, he didn't prove something like full RSB.
No. He just showed. Okay, but I can just say this. He showed that this. He showed that for beta less than beta critical. Okay, let me just strictly less. Let me just for beta less, strictly less than beta critical, the support of mu beta. If I just ask how many points are there, this is just 1 point, and it's actually 0. And for beta bigger than beta critical, then the numbers of points in the support of mu beta, it's bigger than 1, which is enough to say that, oh, you're not delta
Okay.
mass here anymore. Is that okay?
Yeah. Okay, thank you.
Okay, which is very far from this picture. Okay. So 4 times 14 years later, well, we improved a little bit. We can say that not for beta bigger than beta critical, but for beta bigger than 27, something that we can quantify, you have at least 3 points. Still very, very far from what Parisi predicted. Okay. Okay, what is the most recent work? This is myself, Wei-Kuo Chen, and Qiang Zeng. Okay, so this is 20. Is that okay? Maybe I think 19 or 20. Then what we show is that if you send beta to infinity, so you now look at mu beta, but now I'm sending beta to infinity, then the number of points in the support of mu beta, what is this? Okay. Diverges. Okay. So that shows that if you use the physics language, that the model as beta goes to infinity cannot be finite KRSB. Finite KRSB means that the number of points in the support is k plus 1. Okay. So every time you hear 1 RSB, it means that you have 2 points in the support. So what this result tells us is that, okay, you cannot be KRSB, K fixed if the temperature is low enough. Okay. So this is what we call like, oh, the model has infinite levels of replica symmetry breaking at 0 temperature. But it's still very, very far from this picture. Okay. So this was the first theorem that I wanted. Yes.
But then you here at least you could say that the thing is a glass, no?
The thing is a glass. What do you mean?
I mean, if you want to have a glass, somehow you need to have this this fact, no?
Yes.
And so at least you prove that this model is effectively a glass, no?
I agree. But at the same, this is nice. I'm not saying that this is not. This is a really nice result. One of my favorite results. But it's still. My point is that this is still far. It's still like a step away from in a non-trivial step away from what Parisi predicted back in the 70s.
Okay.
All right. So this is the first theorem that I wanted to say, and I'll mention like in 15 minutes how to prove it. It's actually it's a cute argument that I like very much. But now I wanted to say there are many open questions around this. Okay, so this is just one case, and they're also very different phenomena. Okay, so here I'm discussing the case on the hypercube. It's when it went from replica symmetric to full RSB. Okay, so now you guys can tell me if I do now if I go back to the spherical case, then the model is sort of like boring, because what happens is that your replica symmetric just as before. So there is a critical temperature that you just delta mass at 0. But since the Hamiltonian here can be written as just G sigma inner product sigma, I can diagonalize, and the eigenvector is on the sphere. The eigenvectors, it's on my configuration space. So as I send beta to infinity, it's easy to show that what happens to the cube's measure, that you start to concentrate more and more towards the top eigenvectors. Okay, so eigenvectors associated with the top eigenvalues. And in fact, so what happens here is that your replica symmetric all the way, every time you're replica symmetric, except that here are delta mass at 0, and here are just delta mass at q, where this q is changing with beta. And as beta goes to infinity, this q becomes 1, and you just concentrate the top eigenvector. So in some sense, this model is sort of trivial, because you can actually analyze using just random matrix theory. Okay. So what do you do to make this model more attractive? Well, in fact, I could have just started the story there. There is no need that I need to actually just look at the SK model. What is this function? Well, this is a function on my configuration space. It's a Gaussian process that has, if I compute its covariance matrix, I mean, any Gaussian process is just determined by its covariance and its mean. So the mean is 0, and the covariance is, well, if you just compute, that's a calculation. It's in fact R12 square times A. Okay, so it's just the inner product of sigma with tau square. Okay, so I could look at other Gaussian processes defined on this configuration space with covariances that are also a function of the distance, a function of the inner product. Okay, so what you do is, in fact, and again, I could just start like this. You can just look at something that people call the mixed spins, and that doesn't cost much, which is to define Hn of sigma to be a Gaussian process such that the covariance is now a function of the inner product, the normalized inner product of sigma and tau. Okay. Where C here, well, C here is, well, it's a function. And of course, then you need to classify, because not every function will give you something that's quasi-semi-definite. But in fact, these are classified. These functions are just functions that actually can be written as of this form with AP non-negative. Okay, so just you can write down as a polynomial or like a Taylor series with all coefficients being non-negative. Okay, and then the case that I just discussed above, the SK, is the case where this function, what I call the model, is just x squared. Then there is another important model which is called the p-spin. The p-spin is when C is just x to the p. Okay, and then I'll also discuss a third case, which is also simple, is the PQ model, which is when C is just lambda x to the p plus 1 minus lambda x to the q. And what is nice is that these guys, they have different phase diagrams, and pretty much everything is just unexplored. Okay. Okay. So then, so let me just tell you a little bit of predictions, and then I'll just tell you if well, I'm almost running out of time. I should tell you something about the proofs. Okay. So for instance, here for the p-spin, for the pure p-spin, well, this is the pure p-spin. So C equals x to the p. So if I'm doing this on the hypercube, then the picture is as follows. I'll just draw the phase diagram. So there is still always this very first beta critical, which you know that exists. It follows from the work of Toninelli. That here your replica symmetric. Remember, replica symmetric means the solution of the variational problem is just delta mass at 0. Okay. I should have said the Parisi formula exists for all these models. Okay. It exists, and I forgot to mention this is actually a theorem due to Talleyrand back in 2004. Okay. So the variational problem that I described above, it's a theorem. It's something that we know. It's not only a prediction. Okay, so in the pure p-spin, what do you get? You get the replica symmetric at the beginning, but now you have a new phase that you didn't see for the SK model. There is a second value of the temperature, such that here you actually want RSB, meaning that your Parisi measure should be given by a measure that is still atomic, but with 2 atoms. And then after this, you're back to the full RSB picture. Okay, so this is what happens for the p-spin. Everything that is happening here, this is completely open. Showing the existence of this phase, it's a really nice open problem. This second phase transition here is called the Gardner phase, or the Gardner transition. No one knows how to show the existence of this phase. And I say that is extremely nice. Why? Well, because spin glasses are now sort of like not now, but for a long time, they've been the prototype for complex disorder systems. And there is a lot of activity using spin glasses, or at least the theory that coming out from spin glasses to study models of optimization in computational problems or machine learning. There are tons of applications, and this phase they related to possibility of finding or not finding solutions. Okay, for these optimization problems in practice. Okay, so this is a nice open problem. No one knows how to show the existence of this Gardner transition. And again, well, full RSB is still open in the same way. Okay, so this is for the hypercube. Well, it turns out that if you do the p-spin, the pure p-spin on the sphere, then this model is actually solvable. This model is one that I can actually write down everything. This is replica symmetric, still the same thing, but then you get one RSB. And I'll explain why this is, you actually can say everything about this, the pure spin on the sphere. Okay. All right, so then what happens, I'll get to this mixture of two in a second, but in general, let me just make one comment, is that in the hypercube, you always expect, depending on the, regardless of the model, so regardless of the function C that you choose, so here's C, you expect that you get replica symmetric. Then there is a phase in the middle that you don't know what happens, but at some point, you should always be full RSB. Okay. Okay, so here maybe you don't know. In the spherical case, if you take generic C, in fact, for a while, physicists believe that what will happen is that you have, again, replica symmetric. And then here in the end, you don't know what happens in the middle. Again, it depends on the model. But then in the end, you either have replica symmetric, that would be just the case x squared. That's a trivial case. You could have one RSB, just like the pupil spin, or you could get full RSB, just like in the hypercube. Well, this is what was known by the physicists, and this is one of the rare cases where us mathematicians will actually prove a theorem, and the physicists didn't know. Okay, so here's a theorem. This is the second theorem that I wanted to present. This is just with the Qiang Zeng. Is that there exists models of well, models C on the sphere such that the Parisi measure is 2 RSB. Okay, so I'll just say I'll put mu, I'll be slightly, so I need to take beta to infinity. I'll put infinity here, meaning that you can actually write down what the Parisi measure is at in infinity, and then in the end here you end up exactly with 2 RSB. Okay, what is 2 RSB? It means that you have the number of points in the support of this measure is equal to 3. Okay, so that was sort of like surprising. So, and once you have 3 points, then you can have 7, you can have 23. We expect that anything could happen in the spherical case. Okay, and now here's the most recent work, and this is in the last statement that I'll state, and this is the work with Yuxin Zhou. Is that in fact, if now you take on the sphere, that now you know that everything could happen. If you consider the model C to be, again, a mixture of 2 p spins, okay, so P is different than Q. Lambda here is a number between 0 and 1. Then mu infinity, which I'll define in a second now, I'll be precise, is, well, maybe I'll just draw, the theorem will be just a picture. Is, so there are different cases depending on lambda. Okay, so when lambda is equal to 1, you're back to just the pupil spin, and then you want 1 RSB. So you 1 RSB if lambda is less than some lambda critical. Oh, I'm sorry. Then there is a second lambda critical, where here you could either be, depending on the values of P and Q, and now it depends on P and Q, you could be 2 RSB, Or you can be what we now call one full RSB, which I'll explain in a second. Then you move back to one RSB at the end. Okay, what is one full RSB? Is this, well, you have a first jump and then a second jump for the Parisi measure. So this is what we call one full RSB. So you get a characterization of the face of this for lambda bigger than 1. A characterization for the PQ spin model. In the case with the work of Zheng, in fact, this picture that showed 2 RSB, we just found one value of lambda. And we show that, in fact, this is what's happening. And here we can actually classify all possible models that have 2 types of interactions, a P interaction and a Q interaction. Okay, so the point is that this 2 here is actually the fact that you have 2 over there. If you have more interactions, if you now consider a model as more than just 2 types of interactions, then perhaps you can actually prove that there are 3 RSB, 7 RSB, and so on. Okay. What is this mu infinity? Well, it's not only the limit of mu beta as beta goes to infinity, but in fact, if I go back to my original problem, which is computing the max of Hn, it turns out that you can actually prove that the max of Hn, so the ground state, converges again to, so this is a theorem, converges to also a variational problem on the space of, not probability measures anymore, just the space of measures. And mu infinity is exactly the arg-inf of this variational problem. Okay. All right. So okay. So this is 22. What happens in general? What happens for finite values of betas? What happens for generic models? It's just completely open. Okay. So here I'll just emphasize all these questions here are just completely open. The only case really that we know the full phase diagram that it's non-trivial is the spherical pure P spin. It's this case. Okay, so now let me okay, so these are the results. Let me just tell you a little bit how you prove those things.
Maybe I have a small question about this RSB at beta equal infinity. So in terms of the spin landscape, so it means that if you just look at first order, you have a very high multiplicity of the maximum, or?
Yeah, okay, so what happens, so this measure here actually describes the landscape near the ground state, near the global maximum, okay? So maybe I'll just draw a picture. What happens if I just take this mu infinity is just replica symmetric, or maybe just delta mass at 0, it means that my landscape is just convex. It's just really boring. It's just something that looks like this. Okay. If mu infinity is KRSB, then what happens to my landscape is you have, in fact, many near maximum. Okay, and you can actually quantify the actually exponentially many in these models. But not only this, if you compute barriers, okay, so this is my landscape now. Okay, one of them is the global maximum. Okay, I'm drawing minimums here. So here's the global minimum, but there are plenty at very close to the value. But now these barriers are diverging with n. Okay, so then if you want to go from one year, and that's why they create traps, right? So then if you want to go from one year minima to the other, you actually need to jump a diverging barrier. Okay, so this is the case where this mu infinity is atomic. Again, this is the case that you're atomic. In the case that mu infinity is for ISB, This you can prove. This is a theorem. That's a result that I proved back with Wei-Kuo maybe like 3 or 4 years ago with Wei-Kuo Chen. With mu is full RSB, this is still there are things here that are just not known, but what is expected is that your model still have exponentially many near minima or near maximum, depending. But now barriers are no longer divergent. Okay, so now you can actually navigate the model near the ground state. And this navigation has to do with exactly the support. Every time that you have points in support, you can actually navigate using those overlaps. Okay, so this is what this measure actually represents. Okay, it's since you mentioned, I told you at the very beginning that the Parisi measure describes the Gibbs measure. This is extremely well understood. Not only the positions of the Parisi measure, not only the support tells you like overlaps, in a product of points, but also the weights tell you the weights of these clusters of GN. One thing that it's not known here is the role of not only the support, what is the role of the weights of this measure in U? Okay, because we don't have a description of clusters here, so I really at this point we don't know what the measure means. It should perhaps measure how steep it is. But I honestly do not know.
So when you have one full RSB, you know that the support of your measure is exactly the interval between your two atoms.
Between two atoms, yes.
So you have no hole in your supports.
I have no hole in my supports except at two ends. Okay, which has actually a very significant implication to optimization. Sometimes you really want the bottom of the support to be zero. You want this full RSB face to actually touch zero, so they can actually navigate through the whole landscape. As soon as you create this overlap gap, you create hardness in your model. Okay. All right. Okay. Maybe I have like 10 minutes, maybe less. Here is what just to give you an idea how to prove those things. Proofs. All right. So again, the proofs from you could just think, okay, this is just pure analysis. I have a variational problem on the space of probability measures. I just want to say something about the minimizer. Okay. Well, it turns out this is actually extremely hard. There is a reason why this was open for so long. Okay. So what was the insight? What is the first insight? So maybe the first insight is this. Is that there is a nice, really nice theorem by Bouet and Dupuy that allows, maybe I'll be slightly vague here since I'm running out of time and I don't want to tell you how to do things, that allow us to rewrite the determined variational problem that was the hard one. Okay, so this is again, I'm solving, I'll go back to the PDE. So what do I do here? Well, I have this nonlinear PDE. This guy is just the heat equation. If I do a change of variables, then if I do a change of variables, I can actually just transform this this nonlinear term, and then I can actually write down the solution of phi as a function of Brownian motion. Okay, so essentially what you can do is to write down phi also as a solution of using Brownian motion, but as the important thing of the theorem of Bouet-Dupuy is that actually this is given by also a variational problem. Okay, so now it's a variational problem, which I write like this. It's sorry. So phi of 0 is actually expectation here is with respect to Brownian motion is just the expectation of I think here but C of Brownian motion time 1 plus integration from 0 to 1 mu s ds minus 1/2 integration mu square. Yes. Okay, so the first insight is actually just rewrite, and this is actually, it turns out to be extremely helpful. Is to write down this term that we didn't know, which comes from this nonlinear equation in terms of Brownian motion. Once you have this, now you have this double variational problem. Okay, so now you're back to this double variational problem. And then, and then it turns out that you can actually just use. In fact, this problem here is nice. It's essentially convex. It allows you to switch things around. Okay, and then and this double variational problem. Well, we can just write down, or I'll call like this a Fubini version of it. You can do a Fubini for the or mean max. Okay, so this is actually the way that I wrote this should not be inf, this should be soup. But once you do this change, then it actually allows you, well, to prove a few facts, and the facts are just few properties. Number one is that you can actually prove this. You can prove the very first thing that you get for free, which was really hard to prove, but now it's easy. It's just to show the uniqueness that these Parisi measures actually exist and they're well defined. But once you have this new variational problem in this, then what you do is just do very simple thing. You just do calculus. You really just compute, use the fact, the only information that you have is that you want to find the minimizer of this variational problem. The minimizer of this variational problem is the guy that, well, it's the minimum. So what you do, you just do, you differentiate this function with respect to different measures. Okay, and then you do epsilon equals 0. Let's see, with mu epsilon, dg epsilon, right? So it's just, mu epsilon is, I don't know, your mu 0, which is just the Parisi measure plus epsilon some other fixed measure. Okay, so so the trick is this, what really changed the game was just the introduction of this theorem of Bouet and Dupuy. Okay, this is from 2002, and it's a theorem that has nothing to do with Parisi measures. It's just a term about PDEs, and just in the old fashioned, like writing a solution of the heat equation in terms of Brownian motion, or solving the Dirichlet problem using Brownian motion. And here you're just solving a different PDE. But the price you pay is that you get this, instead of just writing down a very simple formula, you actually get a variational problem, which in our case is actually very convenient. Okay, and it turns out that this method is the method actually to prove, essentially all these theorems. Plus, there is another fact that I should mention, is that on the sphere, and this is what makes things also interesting, is that there is a theorem, well, there is a result of Crisanti and Somers. I think this is, this was written by Crisanti and Somers, but as a theorem, it was proved by Talleyrand. Is that you can rewrite, okay, so there is a simpler, this is not the Crisanti and Somers found, there is a simpler version of P beta. And this a simpler version of P beta is so, it's so nice that you can actually write down P infinity in a very simple way. Okay, I'm being very vague here because I'm running out of time. Where you avoid the fact to deal with this nonlinear term. Okay, it's still a nonlinear equation, but it's actually very simple, and it's just functions of integrations of your measure mu. Once you have this Crisanti-Somers formula, it's an easy starting point to actually just do this calculus. Okay, and now how do you prove all these theorems? Well, it's just you can check it's just 10-15 pages of computations. Okay, which again, only way to do it is just sit down and do it. Period. Okay, anyways, this is a story that I wanted to tell today. Sorry, I ran out of time. Questions?
Thanks, Tuca, for a very nice talk. We thank him. And are there questions from the audience?
I have a question about your second variational problem. What's the variable over which you're taking the supremum? No, the one from Bouet and I forgot the other name.
Oh, this one.
Yeah.
Oh, this. Okay, so I'm missing a variable here. I'm swooping over. This is okay. There is okay. I'm sorry. I'm just doing this. There is a new here. There is also second measure, and I'm swooping over new.
And since there is only B of 1 that appears, so you're just averaging with respect to a Gaussian.
Does it make sense?
It does make sense, but oh yeah.
Okay.
So it does make sense, but you're averaging only with respect to B of 1. So why do you have a Brownian motion and not just a standard Gaussian in the average?
Oh, because okay, so maybe this is writing as a okay. So maybe this final result I don't need to. It's not a Brownian motion. It's just a Gaussian random variable. Okay. It's just a Gaussian random variable.
Yeah, I was just wondering if I was missing something.
No, you're not missing anything. The point is that, in fact, you don't want to use. I'm hiding a lot of stuff, right? This is not even a proof sketch that I gave you. I just give you like bullet points. When you actually do this double variational problem, this guy is not very convenient, and in fact, you need to actually use the whole path, the whole Brownian path. And the Brownian path is the one that actually tells you that you start at 1 with log cosh, and you're coming back to at 0. So this is the simpler version of the problem, but in fact, you don't use it. Use the most complicated one and the Brownian representation.
Thanks.
Maybe I could, sorry, yeah, please go ahead. Go ahead, Milton.
Okay, yeah, thank you. So Tuca, what happens if you start to play around with the log cosh and put in there other model generator functions or stuff?
Well, you still have a problem that you can actually just you can analyze. Does it come from a spin glass? Does it come from a problem that we actually have relevance? I don't know. I only look at these functions because there is a motivation to why I look at those. I should mention that, okay, log cosh, when you go from finite beta to this guy, well, log cosh becomes just absolute value. Okay, so there are it's essentially the same PDE, but with different initial condition for different functions. If you work on the sphere, instead of logging cosh, you're just working with x squared. Okay, but our analysis really doesn't, essentially only use the fact that these functions are convex, the initial data. Okay, so if you have a different function, yes, you can walk through, but what is the role of the Parisi measure there? I don't know. Okay, and there is no motivation.
Okay.
Okay.
Yeah, I just had a question. So max HN over N goes to this infimum. So is this P infinity something to do with the large deviations? Or
no. And this infimum has nothing to do with large deviations. Okay, that's the question that people ask. Since as soon as Parisi put out his formula, is it possible to use large deviation techniques to prove Parisi formula to prove this result? That's a big open question. Okay, this inf it's not coming from, and if you hear Parisi's arguments why it's an inf, it's kind of insane. He says that he started with everything as a maximum of k variables, but then k becomes negative, the number of variables. So when you have a maximum of k variables with a k that it's negative, that's maximum is a minimum. So that's what Parisi says. Okay, so it's really hard to actually understand where this is coming from.
Okay, maybe just one more general question. How does this connect with the overlap? You mentioned that at the very beginning. Is there a connection, or is it just obvious? Or
it is kind of it is a theorem due to Talleyrand. When he proved the formula, the very first formula, he proved that when he proved Parisi's formula, he proved that the law of the overlap actually converges to the law of this minimizer. So the law of R12 square converges to. Okay, so it's a theorem. It's it's not trivial. But it's sort of like now it's standard, I'd say.
okay, thank you. Are there other questions? If not, why don't we thank Tuca again? And thanks, Tuca, for a very nice, interesting talk.
All right.
Bye-bye.